Hello students, welcome to a new class, and this class we are going to begin a new chapter by name Catalysis. So we have completed the first unit, chemical kinetics, and the whole unit you will be writing for your internal exam. And the next class, this class we are starting a new chapter by name Catalysis. Okay students, are you ready? Yes. So take a fresh new page and put the heading Catalysis. So before going into catalysis, first we should know what a catalyst is. I think and I hope you all must be knowing the definition of a catalyst. So catalyst is nothing but which speeds up the rate of a reaction. Sometimes it also decreases the rate of a reaction. So we can say it alters rate of reaction or speed of reaction or velocity of reaction. And also students, it doesn't undergo any change in its mass and composition. Okay, it just alters the rate of reaction. So put the side heading catalyst and let us write the definition of catalyst. Okay, right. So catalyst is defined as the substance which alters, in the brackets, decreases or increases rate or speed or velocity of a chemical reaction without undergoing any change in its mass and composition. Once again, catalyst is defined as a substance which alters, that is changes, in the brackets, increases or decreases the speed or rate or velocity of a chemical reaction without undergoing any change in its mass and composition. Written below, write down. This process of altering the rate of a reaction by adding a catalyst or an external chemical substance is called as catalysis. Okay, so the heading is nothing but the process of altering the rate of a reaction by the addition of an external chemical substance, that is catalyst, is called as catalysis. And this catalysis, the term was introduced by a person called as Berzelius, B-E-R-Z-E-L-L-I-U-S, students. Okay, so we have seen it alters, it increases or decreases. Suppose if it increases the rate of reaction, we call it as positive catalyst, and suppose if it decreases the rate of reaction, we call it as a negative catalyst. So kindly first put the side heading positive catalyst. Positive catalyst. So if the catalyst increases the rate of reaction, we call it as positive catalyst. For example, write down decomposition of KClO3, potassium chlorate, into KCl and oxygen. This takes place in the presence of a catalyst, that is MnO2, manganese dioxide, which increases the rate of decomposition of this particular reaction. Hence, MnO2 we call it as a positive catalyst. So write down the reaction, students. 2 KClO3 gives rise to 2 KCl plus 3 O2, and this reaction we call it as decomposition of potassium chlorate. On the arrow you can write down the name of the catalyst. Write down the catalyst MnO2, which is called as a positive catalyst. And also one more example you can write 2SO2 plus O2 gives 2SO3. Here platinum black is the positive catalyst. Okay students, next negative catalyst, which decreases the rate of reaction. Example you can write down alcohol decreases the rate of oxidation of this is what students, CHCl3, chloroform into poisonous phosgene, that is COCl2 carbonyl chloride. One more example for negative catalyst, you can write down students. Rate of decomposition of H2O2 decreases in the presence of glycerol. So this is all very easy to learn, students. So going little bit fast. Rate of decomposition of H2O2 is decreased in the presence of glycerol. So what is the negative catalyst here? Glycerol, right. Okay students, got an idea about catalyst catalysis, positive and negative catalyst? Right. And now students, there is one more type of catalyst, that is autocatalyst. So what is the meaning of autocatalyst? So in the previous reactions we have seen there are reactants and a specific catalyst is to be added to increase or decrease the rate of reaction. But autocatalyst, there are few reactions students in which the products formed themselves act as a catalyst and alters the rate of reaction. So such products which alters rate of reactions are called as autocatalyst. So I have written here the definition. There are few reactions in which intermediate products formed itself acts as a catalyst and alters the rate of reaction. Such catalyst is called as autocatalyst and the process is called as autocatalysis. Understood, ma? There are few reactions in which the products formed or the product formed itself acts as a catalyst and alters rate of reaction. Such catalyst is called as autocatalyst and the process is called as autocatalysis. If you look at the example, you will understand. Write down the example for this. 2K1O4 plus 5H2C2O4 plus 3H2SO4. So this is called as oxidation of oxalic acid in the presence of acidified KMnO4. So here oxalic acid is H2C2O4. It's a dicarboxylic acid, COOH. So its oxidation taking place in the presence of acidified KMnO4. What's the meaning of acidified KMnO4? KMnO4 in the presence of an acid. So H2SO4 is the acid. Okay. So the products formed are MnSO4, KTSO4 plus H2O plus CO2. Okay students, initially this reaction is slow. Once the products are formed, here MnSO4, Mn plus 2 increases the rate of this reaction. That means, so MnSO4 is actually the product being formed in this reaction. And once this is formed, the rate of reaction increases. Why? Because Mn plus 2 from MnSO4 acts as a catalyst and hence it is called the autocatalyst of this reaction. Hope you understood. Right? Next. So below write down. Oxidation of oxalic acid taking place in the presence of acidified KMnO4 is very slow in the beginning. Once Mn plus 2 is formed, rate of reaction increases as Mn plus 2 acts as autocatalyst. So this is all the introduction about the catalysis, types of catalyst students. Okay, positive catalyst, negative catalyst and autocatalyst. Suppose if I give you I can give you 5 questions, you can write answers fatafat on your own, I guess. What is a catalyst? What is catalysis? Who introduced the term catalysis? And what is a positive catalyst? What is the example for positive catalyst? What is negative catalyst? And what is the example for negative catalyst? And what is autocatalyst? And what is the example for autocatalyst? Okay students, clear? Next. Put this side heading, characteristics of a catalyst. Characteristics of a catalyst. Write down. Point number 1. Point number 1. A catalyst remains unchanged. A catalyst remains unchanged in its mass and composition. In its mass and composition, though a change may occur in its physical state, color, etc. Example, coarsely grained MnO2. Do you remember students where this MnO2 is being used? And it is the example for positive catalyst. Yes, it is used in the decomposition of KClO3. Okay. So in the beginning, how it is? It's like coarsely grained. Okay. I think you know the meaning of coarsely grained. So coarsely grained MnO2 used in the decomposition of KClO3 is finely powdered at the end of the reaction. So initially, how it is, students? It is in the form of grains, coarsely grained MnO2. So once it is catalyzing the decomposition of KClO3, what happened? By the time it has come out of the reaction, out of the system, it has become finely powdered. So the change has occurred in the physical state, but no change in its mass and composition. Just there was a change in the physical state. Initially it was coarsely grained. At the end it has become fine powder. Okay, understood the first point? Second point. So generally students, when we are adding a catalyst, we tell you to add a pinch of the catalyst. Okay, so we don't add in large amounts. Okay, so small amount of a catalyst brings an effective change in the rate of reaction. So second characteristic, write down, small amount of catalyst is sufficient to bring an effective change in the rate of reaction. Example, 1 mg of fine platinum powder, 1 mg of fine platinum powder catalyzes a mixture of 2.5 liters of H2 and O2 to form water. H2 and O2 to form water. So how much we are adding, ma? Just 1 milligram of platinum black powder is used to catalyze a mixture of 2.5 liters of H2 and O2 to form H2. Okay. Second one. Third point, a catalyst is highly selective in its action. For example, I went outside locking my main door. So, after coming back, I can open it with my key. I cannot open it with my tenant's key, right? Like that, a catalyst is highly selective in its action. Like a key can open a particular lock. For example, MnO2 is used as a catalyst in the decomposition of KClO3 but not KNO3 or some other substance. Next, fourth characteristic, it only alters rate of reaction. It is not being used up in the reaction, students. How it enters, it just comes out of the reaction in the same way. It might have a change. A change might occur in its physical state or color like that. Okay, it just alters rate of reaction, but it is not being used up in the reaction. Next, fifth one. Activity of a catalyst increases in the presence of other substances called as promoters. For example, molybdenum acts as a promoter for ion catalyst which is used in the manufacture of ammonia, that is Haber's process from N2 and H2. Next, sixth point. So like how its activity is being increased in the presence of promoters, its activity also can be decreased in the presence of some harmful substances even when they are present in traces, students. Okay, and those harmful substances are called as catalytic poisons, and the process we call it as catalytic poisoning. So that is what the sixth characteristic of a catalyst. Kindly write down. It may lose its activity in the presence of other harmful substances even in traces. So this is called as catalytic poisoning. and the harmful substances we call them as catalytic poisons. Catalytic poisons. Full stop. Below write down. Catalytic poisoning is of two types. Catalytic poisoning is of two types. A. Temporary poisoning. Temporary poisoning. So the word temporary itself indicates that, okay, the poison reduces the activity of the catalyst, and when once it is removed, again the catalyst regains its activity. This is called as temporary poisoning. So write down, students. Catalyst regains its activity. Catalyst regains its activity. Regains its activity once the poison is removed or after the removal of the poison. Example, H2S destroys the activity of iron, which is used as catalyst in the manufacturing process of ammonia from N2 and H2. As you all know, this manufacturing of ammonia is called as Haber's process. Okay, so we all know that iron is used as a catalyst and hydrogen sulfide destroys the activity of iron. So once this H2S is removed, iron regains its activity. Okay, so here H2S we can call it as temporary poison. Understood, ma? Next, B. Permanent poisoning. What is permanent poisoning? Even if you remove the poison, catalyst cannot regain its activity. That means the poison will completely destroy the activity of a catalyst. Therefore, it is called as permanent poisoning. Write down. Catalyst does not regain its activity. Catalyst does not regain its activity even after the removal of poison. Even after the removal of poison. So write down example. AS2O3, arsenic oxide, permanently destroys the activity of AS2O3, permanently destroys the activity of platinum, which is used in the manufacturing process of sulfur trioxide from SO2 and O2, which is used in the manufacturing process of sulfur trioxide from SO2 and O2. So these are the two types of catalytic poisoning. Next, put the side heading, types of catalysis. After characteristics of catalyst, students, next topic, types of catalysis, which is a familiar topic for all of you. So, catalysis can be classified into two types. What are they, students? Homogeneous catalysis and heterogeneous catalysis. Write down, catalysis can be classified into two types. First one is homogeneous catalysis. Put the side heading and please underline. What is meant by homogeneous catalysis, students? Do you know what homogeneous catalysis is? Yes. In which reactants and the catalyst are in same phase, we call it as homogeneous catalysis. So please write down, catalysis in which reactants and the catalyst are in same phase is called as homogeneous catalysis. So we can give some examples. Write down below examples. So we can quote in gaseous phase and liquid phase also, students. First we will write down in gaseous phase. That means both the reactants and the catalyst will be in gaseous phase. Example number 1, in gaseous phase, lead chamber process, which is used for the manufacture of sulfuric acid. So in this lead chamber process, NO, that is nitric oxide, catalyzes oxidation of sulfur dioxide. Okay, so 2SO2 plus O2 gives 2SO3. So oxidation of sulfur dioxide, which we come across in the manufacture of sulfuric acid, that too lead chamber process, where NO acts as a catalyst in the oxidation of sulfur dioxide. Okay, so here if we observe, sulfur dioxide, that is SO2, is a gas, O2 oxygen is a gas, and NO is also a gas. So both the reactants and catalysts exist in the same phase, that is gaseous phase. Next, liquid phase, students. Liquid phase. In this liquid phase, we have acid catalysis and base catalysis. Acid catalysis, the meaning acid is used as a catalyst. Base catalysis, base is used as a catalyst. So write down liquid phase. Number 1, acid catalysis. So we can have these two as the examples. First one is inversion of cane sugar. This is sucrose, students. C12H22O11 plus H2O in the presence of an acid. So all these are liquids, ma. Cane sugar solution liquid, water liquid, and sulfuric acid also liquid. Therefore, this comes under homogeneous catalysis. So in this reaction, the products formed are glucose and fructose. C6H12O6, C6H12O6. Next, hydrolysis of an ester. This is ethyl acetate, CH3COO2H5 plus H2O in the presence of an acid. Liquid and also sulfuric acid liquid gives us CH3COOH plus C2H5OH. After acid catalysis, in liquid phase, we have base catalysis. That means the catalyst used in this reaction is a base. The famous named reaction, aldol condensation, students. So, two molecules of acetaldehyde in the presence of a base, it can be either sodium hydroxide or potassium hydroxide. So, NaOH or KOH, this is a base which is used as a catalyst in aldol condensation. So 2CH3CHO in the presence of NaOH or KOH gives us an alpha beta unsaturated aldehyde. So CH3CH double bond CH CHO. This comes under base catalysis. So acetaldehyde is a liquid, NaOH is also a liquid. Okay. Next, second one, heterogeneous catalysis. Opposite to homogeneous catalysis. In homogeneous catalysis, both the reactants and the catalyst are in same phase, whereas heterogeneous catalysis is defined as the catalysis in which reactants and the catalyst will be in different phases. Right? Example. So there we have seen lead chamber process. Here this is a contact process which is also used for the manufacture of sulfuric acid. So here in this process, SO2 is oxidized to SO3 by atmospheric oxygen in the presence of platinum or vanadium pentoxide. There what is used, students? Nitric oxide. So there all three are in gaseous phase. But here SO2 oxygen will be in a gaseous phase, whereas platinum or vanadium pentoxide which exists in solid phase. So write down the reaction. 2SO2 plus O2 in the presence of platinum or B2O5 gives 2SO3. So kindly write down or mention the phases of SO2 oxygen as gaseous phases and PT or vanadium pentoxide in solid phase. Next example, students, hydrogenation of unsaturated hydrocarbons. So, hydrogenation of unsaturated hydrocarbons. Here, alkenes are taken. For example, ethylene, CH2 double bond CH2. Hydrogenation, addition of hydrogen. These two are in gaseous phase. In the presence of nickel, which is in solid state, gives saturated hydrocarbons. For example, in this reaction, we get ethane. So, CH2 double bond CH2 plus H2 in the presence of nickel gives CH3. So, next topic, acid-base catalysis. Okay, students. So far we have seen types of catalysis divided into two types, homogeneous and heterogeneous, and also we have seen the examples. And also students, please mark it as an important question. Most frequently that question is asked. Okay, next, acid-base catalysis. So students, here we can observe that there is a most commonly used acid catalyst and a most common base catalyst. And the acid catalyst, the common acid catalyst, we call it as H3O plus. You know the name of H3O plus, students? Yes, it is hydronium ion. It is the most common acid catalyst, and the most common base catalyst is OH minus ion. What is it called as, students? It is called as hydroxide ion. Okay, so kindly write down those 2 points. The most common acid catalyst is H3O plus, that is hydronium ion, and the most common base catalyst is OH minus, that is hydroxide ion. Full stop. Below write down, students. Suppose if any acid catalyzes the reaction, then we call it as general acid catalysis. Suppose if any base catalyzes a reaction, we call it as general base catalysis. Okay, general acid catalysis and general base catalysis, students. Suppose if hydronium ion, if a reaction is catalyzed by H3O plus, then we call it as specific acid catalysis. Suppose if a reaction is catalyzed by OH minus ion, then we call it as specific base catalysis. Okay. So now, how many points you have learnt? The most common acid catalyst, H3O plus, the most common base catalyst, OH minus ion, and if any acid catalyzes the reaction, then we call it as general acid catalysis. If any base catalyzes the reaction, we call it as general base catalysis. Suppose if a reaction is catalyzed by hydronium ion. So that's why I have written it separately, students, with this highlighting specific acid catalysis. If only H3O plus ion catalyzes the reaction, or you can change the sentence also, students. If a reaction is catalyzed by only H3O plus ion, that means by not any other acid, then it is called as specific acid catalysis. Example, write down, inversion of cane sugar. So just before we have seen C12H22O11 plus H2O. This is cane sugar, sucrose. C12H22O11 plus H2O in the presence of an acid. So acid H2SO4, suppose we are adding H plus HSO4 minus, that H plus added to H2O, it acts as H3O plus, that is hydronium ion. We all know it gives a mixture of glucose and fructose. Next, students, write down, put the next side heading, specific base catalysis. So what will you write under specific base catalysis? If a reaction is catalyzed by, OH minus, that is hydroxide ion, it is called as specific base catalysis. Specific base catalysis. You can write down the example under specific base catalysis, students. Example 2 CH3, What is this CH3, Do you know its name? CH3CHO we have seen under base catalysis example, liquid phase. What is that called as? Acetaldehyde. Now what is the CH3COCH3? It is called as acetone, right? Two molecules of acetone in the presence of hydroxide ion, that is OH minus ion, we get CH3COH. Here OH students, here CH3, CH2CO, CH. This is also an example of aldol condensation in which two molecules of acetone are being taken. Okay, and the name of this compound is called as diacetonyl alcohol. Spelling DIACETONYL, diacetonyl alcohol. Okay students, these are the common things that we learn under acid-base catalysis. Okay, so we have seen general acid catalysis, general base catalysis, specific acid catalysis and specific base catalysis. Next, so inversion of cane sugar. So this is an example under specific acid catalysis. Okay, so we have kinetics of specific acid catalysis in the syllabus students. So kinetics of inversion of cane sugar. So this is the reaction which is catalyzed by H3O plus ion. Okay, so this inversion of cane sugar, if you remember, in chemical kinetics we have learned pseudo unimolecular reactions or pseudo first order reactions. Do you remember? So if you have not yet started reading, please start reading students. Okay, you cannot read the night before exam because it is a chemical kinetics. You have to learn so many derivations. Please don't neglect and please start reading at least okay, from today. Right, this inversion of cane sugar, yes, there we have learned under pseudo first order reactions the example inversion of cane sugar. Even though there are two molecules, that means even though it is a bimolecular reaction, rate of reaction is influenced by only the concentration of cane sugar. Here the concentration of water doesn't influence the rate of reaction. Okay, and why? Because the concentration of water remains constant throughout the reaction and it does not bring any change in the rate of reaction. So only what is affecting the rate of reaction here? The concentration of cane sugar. Hence we call it as pseudo first order reaction. The same I have written here. Right now students, this is a pseudo unimolecular reaction because concentration of water remains constant throughout the entire reaction and it doesn't influence rate of reaction. It can also be called as pseudo first order reaction. Again I have given the definition here once again students. The bimolecular reactions in which the presence of only one molecule influences rate of reaction are called as pseudo first order or pseudo unimolecular reactions. Once again for you, the bimolecular reactions in which the presence of only one reactant or one molecule influences rate of reaction are called pseudo first order or pseudo unimolecular reactions. Next, below write down the rate of progress of this reaction. Which reaction? Inversion of cane sugar. So we are learning the kinetics of inversion of cane sugar. Okay, so how to determine the kinetics of this reaction? Here the rate of inversion of cane sugar or the progress of inversion of cane sugar can be observed by measuring angle of rotation of plane polarized light in a polarimeter. Now here comes the question, what is this plane polarized light? Do you know students what is this plane polarized light? Generally you will be learning this in stereochemistry. Okay, so plane polarized light means generally we all know that light travels in different directions. When this light is allowed to pass through a glass prism, then we observe that light is coming in a single direction. That we call it as plane polarized light. Okay. And now how much this plane polarized light is being rotated, that can be measured with the help of a polarimeter. So the rate of inversion of cane sugar can be noted down or can be observed by measuring the angle of rotation of a plane polarized light in a polarimeter. So here what is the reaction, students? Sucrose on hydrolysis in the presence of an acid, it is being converted into a mixture of glucose and fructose. So if we observe, or if this plane polarized light is allowed to pass through sucrose and the mixture of glucose and fructose, sucrose rotates to some extent and the mixture rotates to some extent. So basing on how much angle this sucrose is rotating the plane polarized, see look here, I have written sucrose rotates. This is PPL, means plane polarized light in one direction, and the mixture of glucose and fructose rotates plane polarized light in another direction. So depending on this angle, we can determine the kinetics of inversion of cane sugar. So below write down, students. Below write down. Let R naught. So this is all we are assuming that the angle of rotation before this much time, after the time. Okay. So just we are assuming. So R naught, RT and R alpha. So first point write down. Let R naught be the angle of rotation in the beginning when time t is 0. Okay. So angle of rotation in the beginning, we have not noted any time, students. Time is not taken into consideration. At that time, let the angle of rotation, we assume it to be R naught. Next below. Let RT be the angle of rotation. Let RT be the angle of rotation after time t. Okay, we can fix some time, 10 minutes or 15 minutes like that. So afterwards, how much is the angle of rotation? That we are considering it to be RT. Next, below write down. Let R alpha be the angle of rotation at the end of the reaction. That means when the reaction is complete. Let R alpha be the angle of rotation when the reaction is complete. Okay. So from this data, in the beginning, after some time, at the end of the reaction. So we have 3 different values. So how to use these values and find the rate constant? So students, this is we know that this is a pseudo first order reaction, and also we have derived the rate constant, expression for the rate constant of a first order reaction. If you don't remember, kindly go back and check for the expression. So here I am taking A as R naught minus R alpha. What is R naught in the beginning? R alpha at the end. So R naught minus R alpha, we can consider it as A. So generally in terms of concentration, we know that A is the initial concentration and A minus X is the remaining concentration. Okay. So A, I take it as R naught minus R alpha, and A minus X, we can take it as RT minus R alpha. RT is angle of rotation after particular time. Now with these values, we know the expression for the rate constant of a first order reaction. What is that, students? K is equal to 2.303 by T log A by A minus X. Do you remember that one? So for a first order reaction, rate constant K is given by, so here you can write, one second students, K is equal to 2.303 by T log R naught minus R alpha by RT minus R alpha. Okay. So in this reaction you write down. log A by A minus X. Okay. So A is R naught minus R alpha and A minus X is RT minus R alpha. This is the original expression for first order kinetics, students. Okay. So in this we can substitute the value of A taken R naught minus R alpha and A minus X taken RT minus R alpha. So from this expression we can calculate the rate constant for the reaction inversion of cane sugar. Okay, students. So hope you understood kinetics of inversion of cane sugar, which is an example for specific acid catalysis. Okay. So this is catalyzed by H3O plus ion, that is called as hydronium ion, and the progress of reaction we are determining by measuring the angle of rotation of plane polarized light in a polarimeter. Okay, students. So learn all the topics which are taught in this class, and also please write down the notes. Don't think that we will write at the point of exam. Okay. So don't do that. Whenever the class is going on, you can please note down all the points in your notebook so that it will be easy for you to practice and study. Okay, students. So this is all for this class today. So we'll meet in the next class with a new topic. Until then, students, please take care, stay safe, and bye-bye.